Okay, it's time to go over some homework. This homework you'll see is from your textbook. I also have the answers to the calorimetry worksheet listed at the end of this PowerPoint as well. This PowerPoint will also be uploaded to the notes, PowerPoint notes folder on the class page, and you'll also be able to obviously access this through YouTube if you want the explanations. So let's get started. The first set of problems that you had were from page 507, and they were numbers 1 and number 2. And this just wanted you to look at an example and decide if something was exo or endothermic, and talk about direction of heat flow. So in number 1, you have a container of melted paraffin wax, and it's going from a liquid to a solid. And when something is solidifying, it's getting cooler, so that means heat is leaving. So the reaction would be exothermic because it's giving off heat. In number 2, it's talking about a beaker of reaction that occurs between between barium and ammonium compounds, and it says it becomes very cold. If a reaction becomes very cold, that means the temperature's dropping and heat was absorbed into the system. So that would be endothermic. Okay, these two questions are from page 510 in your textbook, numbers 3 and 4. And so we're going to take a look at the math for these particular problems. The first one's asking for specific heat. So if I'm to calculate specific heat, I'm going to be looking for C sub P. So I'm solving for C sub P, and the equation is going to look like this. And if I look back up in the problem, let's highlight what we know. We know Q is 435 joules. We know mass is 3.4 grams. And then our initial temperature is 21 degrees C, and our final temperature is 85 degrees C. So now I'm just going to plug in the numbers to this equation. Whoops. Let's go back to the pencil there, or the marker. And so I have 435 joules in the numerator, and my mass is 3.4 grams, and I'm having a temperature change of 64 degrees C, and so my final answer ends up being 2.00 joules per gram degrees C, like that. Now number 4, it says how much heat is required to raise the temperature. So I'm looking for Q in this one. So Q equals mass times C sub P. And I'm going to plug in the things that I know. The mass is 250 grams. I'm going to multiply that by the C sub P, which I got from a table in your textbook, and that's 0.14 joules per gram degree C. And I'm multiplying that by the temperature change, which was 52 degrees. I'm going to multiply all of those together, and I get 1,820 joules. I believe the question asked for, it didn't ask for that. I thought maybe it asked for it in kilojoules, but you could convert this to kilojoules, and that would be 1.8. Just divide by 1,000 to get your kilojoules for that one. I'm keeping it to 2 sig figs because the temperature was in 2 sig figs. If you went out to 4 sig figs, that's fine. I'm not being extremely picky with the sig figs, but I am going to try to follow them in the problems. What I did here was I put the questions 3 through 11 from section 17.1 assessment, and then right below it I put the keys. So you might want to just pause the video so that you can look at your answers and compare them to the answers that are shown on the screen. 9, 10, and 11 are math problems, and in number 9 you're going to be using Q equals mass times C sub P delta T to solve for that. And then in number 10, that one I actually want to do the math. I think you can figure out number 9. If not, let me know and I can explain the work for that one. But that one's just a plug and chug. But number 10 is saying that you have silver that has a heat capacity. Remember, heat capacity doesn't include mass. Specific heat is where we include mass. So they want you to take that heat capacity, and you know that you have a chunk of silver that's 181 grams. And all you're going to do is divide the, let me just write it in here for you, the 42.8 divided by the mass. And this is joules. Hold on a second. Joules per degree C. No mass there, but we're going to add the mass now. Just divide by the 181 grams, and that gives you a specific heat of 0.236 joules per gram degree C. So that's all you had to do for that one. And then the last one, it says how many kilojoules of heat are absorbed when 1 liter of water is heated from 18 degrees C to 85 degrees C. For this one, you're going to have to convert that 1 liter of water to grams, and you'll have to use density for that. So you end up let's see here, you end up taking the 1 liter, multiplying it by 1 liter to 1,000 milliliters, and then you, I can't fit it in here, but you would multiply that by 1 gram per milliliter. So then liters cancel, milliliters cancel, and you're left with 1,000 grams. And now you can take that mass and you can use it in the Q equation. So let me just change colors here so it shows up maybe over top of that purple there. So now I'm going to have Q equals the 1,000 grams. I'm going to multiply it by the C sub P of water, 4.184 joules per grams degrees C, and the delta T would be 85 minus 18, and that gives me 67 degrees C. And my answer then for that, well, that doesn't look so great on the screen, but the answer for that one in kilojoules, after you do converting, is 2.8 times 10 to the second kilojoules. Okay, so that's the work for number 11. Okay, for these conversions, I'm going to just put the equation down, or the conversion that I used. So for A, we were going from 8.5 times 10 to the second calories, and we're going to the big calorie. So 1 capital C calorie is 1,000 little c calories. And I have the answers already shown to you off to the right of the problem, so you can just look at the answer there. For B, we're going from calories to joules, so 444 calories, and we want to go to joules. Funny story, my dog just came in my bedroom, and he is sitting right next to me while I am giving you these answers to these problems. And it's very cute. That doesn't happen in the classroom, but it happens when we're doing online classes. Okay, so there's the setup for B. Calories are going to cancel. I'm left with joules. And letter C, we're going from kilojoules to joules, so 1.8 kilojoules. And there's 1,000 joules in 1 kilojoule, so that's the setup for C. And then the last one, the setup for D, we're going from kilojoules to joules to calories. So we want to go kilojoules to calories. Oh boy, I'm not going to have enough room here, so I'm going to have to do this in steps. Okay, the first thing we want to do is the 4.5 times 10 to the negative 1 kilojoules. And we're going to convert that to joules. Kilojoules will cancel. I'm left with joules, and then I want to take joules to calories. So 1 cal over 4.184 joules. Joules cancel. I'm left with calories. So that's the setup for letter D. Also, the answers to 42 and 44 are there as well. No math involved in those, but the answers are off to the right. Okay, just quick explanations here. Obviously in 46, anytime something is reacting and it becomes hot, we know it's exothermic. And then in 47, I would like to kind of focus in on the condensing and the evaporating. Those are phase changes, and when we're condensing, that means we are going from a gas to a liquid. And when we go from a gas to a liquid, that means the temperature is decreasing. That means I'm giving off heat. It's releasing heat to go back to a liquid. So A would be exo, and that's why A is exo. And B, when we're evaporating alcohol, we're going from a liquid to a gas. So we're doing the opposite. If we're going from a liquid to a gas, it needs to absorb heat from its surroundings in order to raise the temperature of the alcohol to evaporate it. So if the temperatures, we need to increase the temperature. That means we're absorbing heat, so that would be endothermic. So that's just a quick explanation on 47A and B, because they're phase changes. Obviously, if we burn something, that's exothermic in letter C, and then D, baking a potato. Again, we're raising the temperature, we're adding heat to the potato, so it's absorbing heat, and so that would be endothermic. Okay, this one I am going to highlight some important things in this particular problem. This is 12 and 13 from page 513. The amount of water we use, the 50 mils, is important, so I'm going to highlight those two. Now remember, I said this before when we were looking at practice problems, the moles of hydrochloric acid and sodium hydroxide are so minimal, they're not going to affect the mass of the water at all. So we don't need to worry about those two moles or concentrations of those two. We are interested in temperatures. Both of them start at 22.5 degrees C when they're mixed together, which is about room temperature, and the temperature increases to 26.0 degrees C. And we want to know how much heat, and it does say in kilojoules, was released in this reaction. So what we know here is the C sub P of water, so let's just write that down, 4.184 joules per gram degree C. We also know the mass of the water. We have 50 grams. Remember, I just can take the milliliters, as long as it's milliliters. If it's liters, I have to convert to milliliters. But I can take the milliliters and convert it right to grams. I'm multiplying by the density of 1, so I'm not going to show you that math because we've done that before. And so I have 100 grams of water. So that's my mass. And then my delta T, the temperature is increasing, so my final temperature is 26, and my initial temperature of the liquids was 22.5, so my delta T is 3.5 degrees C. Now I'm just going to plug those into the, sorry if you hear my dog making noise, he's rolling over and sighing in his sleep. It's very cute. I'm just going to multiply all of these things together. So I'll write this out for you. Sorry I'm leaving some of the units off because I'm trying to go quick so you guys aren't sitting and listening to a video. Okay, and when we multiply those together, we get 1464.4 joules. We want kilojoules, so let's move that decimal 1, 2, 3, and that's going to equal 1.5 kilojoules. I went to 2 sig figs because the temperature is in 2 sig figs. So that is number 12. Number 13 is the same kind of setup. Let's take a look at what we have. We know a pebble is being heated and then put in a foam cup calorimeter. We have 25 mils of water. We know that can be 25 grams. The pebble temperature changes from 25 degrees C to 26.4 degrees C, and they want to know how many joules of heat were released by the pebble. So I'm going to do the same setup. I'm going to take Q. I know the mass of the water is 25 grams. I know the specific heat of the water is joules per gram degrees C, 4.184, and my temperature change is going to be these 26.4 minus 25, and that gives me a temperature change of 1.4 degrees C. When I multiply all of these things together, I get 146.44 joules, and I would go to 2 sig figs, so 150 joules. And that would be the answer for number 13, the work for number 13. And here's the answers for 48 to 51 from your textbook. Again, there's no math here, so I just put the answers for you right below the questions on this slide. And then the last thing that I have here are the answers to the worksheet problems. So take a look at those. For number 4, the setup for number 4, you had to use negative Q of the metal equals Q of the water. So you have to set up these two equations to equal each other. So you would have negative mass C sub P delta T of the metal, and the water on this side you would have mass C sub P using C sub P of the water on that side. So the mass of the metal was 24.7 grams. So that's how you had to set that one up, plug in the numbers, everything that you know. Number 5 was a challenge problem. So that one you should have gotten an initial temperature of 36.4. Again, this is going to be set up the exact same way. So let me show you the work for that one so that you have, so you know how that one was solved. I'm just going to erase this to give me some room. And we will, you should have your worksheet handy so that you can see what I'm doing here. So I have negative the quantity of the mass C sub P delta T. That's going to be for the metal. Because the metal, the temperature is decreasing, so the temperature is going to end up being a negative, the delta T will end up being negative, and that's why we need the negative on the outside of that quantity. The water side, the delta T ends up being positive, so we don't need to worry about the negative in front of that side. So let's plug in what we know. The mass of the metal is 2.5 grams. The C sub P of the metal is 0.390. And again, I'm not using units right now, just to save time and space, really. And then I don't know, I know what the final temperature is, but I do not know what the initial temperature is. So I'm just going to plug in Ti. And then I'm going to close my bracket, and I'm going to set it equal to what I know about the water. And what I know about the water is, okay, the water side, we have 65 grams of water. And C sub P of water is 4.84 joules per gram degree C. And the delta T, I know here we're going from 22 degrees C to 22.5 degrees C. And so our temperature change is only half a degree. And now we're going to solve for Ti. So what I did is I multiplied, this is a challenging algebra problem. So what I did is kept the negative sign here. I multiplied these two quantities together, and that gave me 0.975 multiplied by the quantity like so. And then I multiplied through everything on the other side and got 13.598. And that's going to be joules. Now I use the distributive property. Let me just put brackets around here so we don't get lost with that negative sign. I'm going to move up to the top of the page to finish this problem, so bear with me, I apologize. Now I'm going to take the quantity 0.975 and multiply it through what's in parentheses. So I end up with negative 21.9375 plus, and that plus comes from this negative sign and that negative sign. When I multiply them together, they become positive, and so I have a positive 0.975 Ti, like so. And let me rewrite that. I don't like the way that that's, I don't have enough room, and I don't want to confuse it. So I have negative 21.9375 plus 0.975 Ti, and that's equal to the 13.598. That's just going to keep moving down. Now I can combine like terms on both sides and solve for Ti. So I add 21.973 to both sides, and then I end up with 0.975 Ti on this side equal to 35. And notice I'm writing out all of the digits because of rounding at the end. I don't want to round twice. And then I'm going to divide by 0.975, and when I do that, I get 36.4 degrees C. You could follow the units all the way through there. They do work out. But just to save time and to save space, I kept some of the units out. But you should get degrees C if you follow the units through. So that's how we solved number 5. That was the challenge problem on the worksheet. Okay, I hope this was helpful. Again, if you have any questions or you're unsure of something in this particular homework review, just send me an email or ask a question in the forum, and I'll be sure to get back to you. Also, this PowerPoint, if I didn't mention it before, will be in the note folder on the class page. Obviously it won't have all of the answers in it, but at least you can go through and you can look through the questions and the book answers, so you have access to that as well. Okay, hope this was helpful. See you next time.